All right, to section 2.6, limits involving infinity, asymptotes of graphs. So we're going to finally put a calculus meaning on this infinity symbol. You've encountered, probably so far, the infinity symbol, a sideways 8, to represent intervals, unbounded intervals. For example, the whole real numbers could be represented as the interval from negative infinity to infinity. I'll critique that terminology here shortly. The non-positive real numbers, all x such that x is less than or equal to 0, can be represented as this interval with an infinity symbol in it. The interval from negative infinity to 0, including 0, with the little square brackets. 7 to infinity, with parentheses, this open interval, is all real numbers x such that x is strictly greater than 7. No square bracket on the left-hand side, so no inclusion of that endpoint. Quick comment, and there's some comments about this in some of the appendices as well. This interval has one endpoint, doesn't include the endpoint, but 7 is an endpoint. There is no right-hand endpoint. This interval has one endpoint. It has a right-hand endpoint, no left-hand endpoint. It includes that right-hand endpoint of 0. And here's an interval that doesn't have any endpoints. Infinity, as the text says, infinity is not a number. We won't do arithmetic with infinity. There's not an infinity place, even though I might read this as the set of all real numbers from 7 to infinity. There is no to infinity. Buzz Lightyear has misled you. There is no ad infinity. Now that terminology may come up in expressing these symbols. I mean, words are a weak substitute for symbols in math. So there may be some reading of these things as to infinity, but conceptually there ain't a place infinity on the real number line. Not a number. Not something you'll do arithmetic with, therefore. You won't talk about infinity plus infinity at any stage as an actual numerical operation. For us in calculus, infinity is a limit. So beyond this application in terms of unbounded intervals, we'll see the infinity symbol used to represent limits. And we might talk about infinity minus infinity, indeterminate forms of a limit, but that's a conversation not about arithmetic, but about limits. More of that if we do L'Hopital's rule in Calculus 1. You'll do it in Calculus 1 or 2, depending on how the book's laid out. You're familiar with a formal definition of limits by this stage. So we'll give a formal definition when we encounter these infinite limits ad infinity, the book will call them. You know, I'm going to object to that word at right there. We won't do the anthropomorphic thing of what the function tries to do. There is no close to infinity, for one thing, so the function can't try to get close to infinity. I'll have some problems in terms of some of the terminology we had from the other settings of limits with the anthropomorphic stuff. All right, we will do a little informal job, but let's start with a formal definition of limits at infinity. At infinity. It means what we're about to say it means. Let f be a function such that for all real numbers p, the domain of f includes an interval of the form p to infinity. Sorry, for some real number p, includes the interval from p to infinity. So the function's defined for large input values. How large? Well, this some number p determines how large you have to go before you're ensured that the function's defined. Just like we wanted functions defined close to c, here we want functions defined on intervals of this sort. That includes x values that are big. Think of it that way. They're not close to infinity. That's meaningless. They're big and positive. We say that f of x has the limit L as x approaches infinity. Okay, this means what we're about to say that it means. And we write the limit as x approaches infinity of f of x equals L. That's how that's read. If for every number epsilon greater than 0, there exists a corresponding number m such that for all x satisfying x is greater than capital M, that implies the absolute value of f of x minus L is less than epsilon. Okay, that looks rather similar to our definition of limit in the past, formal definition, except here there's no delta, but there is an epsilon, and you think of epsilon as being arbitrarily small. So we're saying something or other implies the distance from f of x to L is less than epsilon. You can make the distance from f of x to L arbitrarily small. Before is probably a slightly more complicated story, you had to make x sufficiently close to a C value before in section 2.2, 2.3. Here, we're trying to make x big. So there's not a delta, but there's a capital M. Think of M as big. And we're saying, provided x is bigger than M, then f of x minus L, distance of, is less than epsilon. So you can make f of x as close as you want to L by making x sufficiently large in the positive direction. And informally, that's how we'll describe it. But there's the formal definition. The only difference from what we had in the past is the delta stuff has been replaced with capital M stuff. And now we're requiring x to be bigger than capital M. It's this stuff highlighted that is requiring x to be big. How big? Well, bigger than capital M. If we wanted to take a limit in the negative infinity direction, two directions on the real line, let f be a function such that for some real number p, the domain of f includes the interval negative infinity to p, meaning now that function's defined for large negative x values. We say that f of x has the limit L as x approaches negative infinity, written and read the same way we just stated that. Limit as x approaches negative infinity of f of x equals L. If for every number epsilon greater than 0, there's a corresponding n such that for all x less than n, we get the distance from f of x to L to be less than epsilon. So this time you want to think that n is maybe a large negative number. And we're making x then a larger in magnitude negative number. There's no close to negative infinity. We're making x sufficiently big in the negative direction is what this n stuff is about. So if we wanted to go slightly more informal, sufficiently and arbitrarily, then we'd say something like this. First, the usual setting, let f be defined on an interval p to infinity for some real number p. So x is defined for big positive x values. We say the limit as x approaches infinity of f of x equals L if, informally, f of x gets arbitrarily close to L, that's the epsilon part, as x moves sufficiently far from the origin in the positive direction. The book words this slightly differently. I like the sufficiently. So I see arbitrarily close and sufficiently again. Before it was arbitrarily close for x sufficiently close to C. Here, x is going to infinity. There isn't a close to infinity. So I don't say sufficiently close to infinity. We'll say sufficiently far from the origin. How far? Well, that was the capital M parameter, the capital M parameter, when x was approaching positive infinity. And similarly, if we wanted to take a limit as x approaches negative infinity, we'd require the function to be defined on an interval of this sort, or else limits don't make sense when the function doesn't include appropriate values in its domain. And we say the limit as x approaches negative infinity of f of x equals L. Notice we picked up a little negative sign right there on that infinity. If f of x gets arbitrarily close to L, that's the epsilon part, as x moves sufficiently far from the origin in the negative direction. And that's the capital N part. Let me scroll back up. In the first one, we wanted x to be greater than capital N, so big and positive. And in the second one, we wanted x to be less than N. Think of N as a big negative number. It can be any number in particular, big negative numbers. We want x to be less than capital N. So up here, big and positive, down here, big in magnitude, absolute value, and in the negative direction. So far from 0 if these are numbers big in magnitude. Big in the positive direction in the first case, big in the negative direction in the second case. Again, we'll write these arrows. X approaches infinity or x approaches negative infinity. We don't mean x gets close to infinity. There's no infinity on the real line. We've described it in terms of moving sufficiently far from the origin in the positive or the negative direction in those two informal ideas. It's read x approaches infinity or x approaches negative infinity, but there is no approaching infinity. There's no infinity there. What the infinity idea means in this setting is rigorously what we said upstairs. And informally, it means getting far from the origin in the positive direction, if we write this, or in the negative direction, if we write this. Sometimes we may have x approaching positive and negative infinity. So it's a claim about two limits. A limit as x approaches positive infinity and a limit as x approaches negative infinity. A quick little observation, it is tradition, at least in this book, when x approaches positive infinity, not to write the little plus sign. You want to write the little plus sign there, you go right ahead. I certainly can't argue with that. I had actually edited my notes and had some pluses in some places and not in others, so I took the pluses out to make it consistent. But it's a very reasonable thing to put a plus sign in front of the infinity here. Down here, if we're considering x approaching positive infinity and negative infinity, oftentimes functions will have the same behavior in both the positive and negative infinity directions. So we'll consider x approaching plus and minus infinity as a single problem. Let's illustrate that rigorous definition, kind of trying to get more informal stuff done. But we've got a rigorous definition. Let's illustrate it at least once. Let's prove that the limit as x approaches infinity of 1 over x equals 0. Okay, that makes perfect sense. You're taking a reciprocal of a big number. I expect to get a little number. I can make that big number arbitrarily big. Then I can probably make 1 over x arbitrarily small. That is arbitrarily small in magnitude. I can make it as close to 0 as I want by making x sufficiently large. So let's go through a proof on that. This will be a case of find capital M. X approaches infinity, find capital M will be the puzzle in this one. Okay, so to the supplemental notes. Prove that. Well, first, notice that this function's defined on an interval of the form p to infinity. We take p to be 0. Take p to be 100 if you want. You take p to be 1 billion if you want. We just need an interval of this form on which the function is defined. Might as well take 0 to infinity. That'll work. It isn't defined at 0, but we excluded 0 from that little interval. So the function is defined for x big and positive. That's what we need when we talk about this kind of limit. So let epsilon greater than 0 be given. We're still trying to get f of x close to L. F of x is the function 1 over x. The rumored L value is 0. So now the question has become, how big do you have to make x, capital M equals what, in order to make 1 over x within a distance of epsilon of 0? we must find a number, capital M, such that when x is greater than m, that implies f of x minus L is less than epsilon. Our f of x is 1 over x, our L value is 0. So we could simplify that to 1 over x is less than 0. This implication will hold. The claim is when m equals 1 over epsilon or anything larger. You buy that? How would I relate these two inequalities? You want to see a 1 over x. Okay, we take a reciprocal of both sides of this inequality. Take a reciprocal, that's going to reverse the inequality, provided everything's positive, and it is. X is positive, m is positive, without loss of generality, if you like. But m is a positive number as well. So take reciprocals, and that would give 1 over x is less than 1 over n. So it seems like we need to take the m value equal to 1 over epsilon, or the 1 over m equal to epsilon. Here's how we'd express m in terms of epsilon. But anyhow, in the square brackets here, we're kind of scratch working our way through this to choose an m value. We're going to use m equals 1 over epsilon. Let's look at a picture. So you sure about this? Yeah, here's a graph of 1 over x. Actually, it's a hyperbola with axis that's at 45 degrees to the x-axis, but it's a hyperbola. And it's got a couple of asymptotes here. Okay, 1 over x, we're trying to get that within epsilon of 0. Here's 0. If we go epsilon up and epsilon down, we'd get a yellow band that ranges from here to here. Okay, so picture out of the book, I'd do it slightly differently and make this yellow band run all the way from negative epsilon up to epsilon. They've capped it below at 0. I mean, I know the function's never going to dip below 0 when we look at the right-hand half. Similarly, it's never going to go above 0 if we look at the left-hand half. We're having a conversation about the right-hand half. Here's epsilon. All right. In this case, we would want this function to lie within 0 of epsilon. We want it to be within this yellow band, starting at some point and to the right of that point for some particular x value and from the right onward. So there's not a little green box this time. There's actually a little green band, forgive me, that goes to infinity. It's unbounded on the right is what happens. So for this given epsilon, when does that curve dip below here and lie inside that little infinite green band? Well, it starts right here, when the function produces a value of epsilon, when the y value is epsilon. If epsilon equals 1 over x, what does x equal? 1 over epsilon, the input would have to be 1 over epsilon. You take the reciprocal of 1 over epsilon, and indeed you get epsilon out, like you should. So we'll take that to be the m value. And that's what we set over here, and you can see from the picture, this is very similar to what we did when we did regular all limits as x approaches c of f of x equals L. Same idea, except we get this unbounded green band instead of a little green box. Hey, because x could be anything as big as m, well, anything strictly bigger than n is how we set it up. So that means this box is going to be unbounded to the right. We're considering a limit as x approaches positive infinity of 1 over x. Were we to consider a limit as x approaches negative infinity of 1 over x, we'd find the n value in a similar way. In that case, we use the symbol n. And now the little box would stretch towards the left, unbounded. So we need to confirm that when x is greater than m, when we suppose this, we want to show f of x minus L is less than epsilon. So it starts here from the definition, and we're drawing this conclusion. So let's just confirm the computations. Suppose x is greater than m. We chose m to be 1 over epsilon. You choose m, you choose n. You got no control over epsilons, just like in the old stuff. M is, in a sense, playing the role of delta. Okay, x is greater than 1 over epsilon. All right, let's take reciprocals. that'll give us a 1 over x, a 1 over m, and an epsilon. But a reciprocal, and here's the reciprocal function right here. Notice it's a decreasing function when we input positive things. So we input anything, it's a decreasing function. But let's concentrate on the fact when we input positive things, which is what we're doing. We're taking m to be positive. We're taking x as positive. So when we take reciprocals, things get smaller. So the inequality gets reversed from x less than m to 1 over x, from x greater than m to 1 over x less than 1 over m. We took reciprocals and reversed inequalities. Remember, we were taking x to be positive, so we can actually bound that below by 0 as well. And let's see, 1 over m is the same as 1 over epsilon, is the same as epsilon. So what we have here is 1 over x is greater than 0 and less than epsilon. We've assumed x is greater than 0 in all of this. We've got 0 is less than 1 over x. We can take 1 over x and let's write it as the absolute value of 1 over x minus 0. Why would you do that? Because I want to see f of x minus L. And 1 over x is f of x in this problem, and L is 0. So write 1 over x minus 0, absolute value of. Sure those are equal? Yeah, well, the 0 doesn't do anything, but I want to put it there so I see this. Let's put the 0 there. And so this is really the absolute value of 1 over x. Remember, x is positive, or 1 over x is also positive. So I can drop the absolute values. You can't just willy-nilly drop absolute values. You can drop them if you know enough about the input values to drop them. If I know the input stuff is positive, like we do here, then I can drop the absolute values. If I know the input stuff is negative, it takes a little more engineering, but I can, if I'm careful enough, drop absolute values then as well. I replace them with negative signs. Is what happened. We'll see some of that in some of our manipulations today. But these are in fact equal, and what we've got then is the absolute value of f of x minus L is less than epsilon. Excellent. That's the very definition of the limit as x approaches 0 of 1 over x equals 0. Say that correctly, limit as x approaches infinity, positive infinity of 1 over x equals 0. Could you do the same thing for a limit as x approaches negative infinity of 1 over x equals 0? That's part B of this example. And the picture tells you what to do. You'll choose capital N to be negative 1 over epsilon, and off you go. Things will get a little bit more interesting down here when you have the absolute value in that case, but very similar. It'll fall through. It's in the book. Back to the notes. Okay, I can't really express my excessive joy over the establishing of this thing. The limit as x approaches infinity of 1 over x equals 0. And its sibling, the limit as x approaches negative infinity of 1 over x equals 0. There's your proof for part A in the notes. Part A and B are in the book. See example 2.6.1 part B for this second part. That's fundamental. And I want to say all the infinite limits will evaluate. I'm just a little scared to. We're going to use this a bunch. I can't offhand think of any limit as x approaches infinity that won't ultimately take advantage of one of these two things here. So this is fundamental when we actually go through and start computing these things. The stuff we know from the past about like regular limits, x approaches c kind of things, we had Theorem 2.1 with, what was it, like 7 different properties of limits as x approaches c. These also hold as x approaches positive infinity, and these also hold as x approaches negative infinity as follows. So this is just a little restatement of Theorem 2.1, but this time we've got x approaching positive infinity or negative infinity. Suppose the limit as x approaches plus or minus infinity of f of x equals L, and the limit as x approaches plus or minus infinity of g of x equals m, respectively. So this is really 4 hypotheses. X approaches positive infinity, X approaches negative infinity, X approaches positive infinity over here, and X approaches negative infinity over here. So it's really 4 statements there, 4 sets of hypotheses. Then the claim is the limit of the sum is the sum of the limits, just like we had before. I didn't write it out quite as explicitly here. The limit of the difference is the difference of the limits, even though they involve X approaching plus or minus infinity. Limit of the product is the product of the limits. You take a scalar multiple times a function, you can bring that scalar out front. Limit of a quotient of the limits. Again, if you don't get 0 in the denominator. Limit of a function raised to a power is the limit raised to that power, L to the n. And the limit of the nth root is the nth root of the limits, where we're real careful about square roots of negatives, as we were back in Theorem 2.1. So Theorem 2.12, is it? Yeah, 2.12 basically says those rules you had in Theorem 2.1 about like regular limits, they all hold under appropriate hypotheses for limits as x approaches plus or minus infinity. All right, when we're dealing with limits as x approaches plus or minus infinity for rational functions, and we'll probably have more examples related to rational functions than other functions, but we'll have examples related to other functions as well. But if we have a rational function or something that's kind of related to one, it turns out, we'll first divide the numerator and denominator by the highest power of x in the denominator. Highest power of x in the denominator. And then we'll use the 2 things we know. The limit as x approaches plus or minus infinity of 1 over x equals 0, if I write that as a single type expression. Let's do it in a couple of examples. So let's look at 2.614, an exercise from the homework section. Here's your rational function, a ratio of polynomials. F of x equals 2x cubed plus 7 over x cubed minus x squared plus x plus 7. Find the limit as x approaches positive infinity, x approaches negative infinity. Justify your computations using that theorem we just stated. Okay. Turns out, as you'll see, we can evaluate both of the limits by the same process. So we're going to consider a limit as x approaches positive infinity and negative infinity at the same time, unless something goes wrong. You have a rational function, nothing will go wrong. You got a ratio of polynomials, you can do these limits as x approach positive infinity and negative infinity together. Okay, f of x we'll substitute in. Here's f of x is copied from upstairs, and the note said divide the numerator and denominator by the highest power of x in the denominator. Denominator's got an x cubed in it. So let's divide the numerator and denominator both by x cubed. That is, let's multiply by 1 over x cubed divided by 1 over x cubed. That's 1, ain't it? Unless x equals 0. Does x equal 0? Can you tell me what x is? You can tell me x is approaching positive infinity or negative infinity. What's that mean? Well, it means x ain't 0. And all limits don't really tell you what x is specifically, but it does tell you what x isn't, in a sense. X is not 0. I mean, the idea is x is big in positive or big in negative, big in magnitude and absolute value. Well, if it's either of those, it ain't 0. So we haven't divided by 0 here. Very mindful of that because I can't divide by 0. Let's see, we'll do the multiplication here and some distribution. All right, so I'll copy this on the next slide. Yeah, okay. So we've distributed. Can we cancel? Can I cancel those x cubes? Tried to get you ready for this. Yeah, as long as x isn't 0. Hey, x is approaching plus or minus infinity. We can assume it ain't 0. We can assume it ain't 7. We can assume it ain't 7 gajillion. It's bigger than that when x approaches positive infinity, say. So yeah, we are justified in saying x is not 0, and we can cancel these x cubes. We can cancel these x cubes, are gone. Here we got an x squared over x cubed. Cancel, that leaves you with what, a 1 over x. a 1 over x squared here, and well, there's nothing to cancel there. So do that cancellation of the x values, all right, justified by the fact that x is non-zero. And what do you see that catches your eye? Well, it ought to be a bunch of 1 over x's. And you know what 1 over x does. You don't know much about limits as x approaches infinity, but we've established one thing. 1 over x goes to 0. And that's the reason we divided the numerator and denominator by the highest power of x in the denominator, to get all these 1 over x's. Now we just got to get the limit from over here onto those 1 over x's. So that's the strategy, and that's what comes next. Taking a limit of a quotient, why, that's the quotient of the limits, says Theorem 2.12, Part 5, the quotient rule for infinite limits. Assuming the denominator is not 0. So if we end up getting zeros in the denominator, we're going to come back to right here because we've done something wrong if that happens. It won't happen. That's the reason you divide it by the highest power of x in the denominator. You won't, if you do that, you won't have division by 0 in this process. Okay, we've got a limit of a sum and a difference in the denominator. So let's use those properties to put the limits on each of the constituent parts, justified by the sum and difference rules, Theorem 2.12, parts 1 and 2. You didn't distribute that limit, when it looks like it, but you didn't distribute that limit. Distribution is something you do with multiplication. And this ain't multiplication. This is a taking of a limit. All right, so it looks like distribution, but it's not called distribution. It's Theorem 2.12, parts 1 and 2 is what it is. It's the sum rule and the difference rule. So that gets the limits on to each of these. Let's see. I got a constant of 7 here and a constant of 7 here. We can bring those constants outside those limits, can't we? That's what's done in the next step. Let's actually look at it on the next page. Yeah, we can bring that 7 outside, and we can bring that 7 outside of those limits. That's the constant multiple rule. Trying to get limit of 1 over x. Do you have that? There's one of them. So I'm happy with that one. I got a 1 over x cubed here, and a 1 over x squared there. Well, we can deal with that. We can use the power rule, which says the limit of 1 over x cubed is the same as the limit of 1 over x cubed. Effectively, I can take that limit inside that cubing function. The power rule tells you that. So we take limits inside and get the cubing on the outside here, and the squaring on the outside there. So we've used the power rule actually in 3 different places on that one. And we're good to go. Do you know what the limit as x approaches positive infinity of 1 over x is? Yeah, we proved it's 0. Do you know what the limit as x approaches negative infinity of 1 over x is? Well, we claimed it was 0 and that the proof is similar to the proof when x approaches positive infinity. It was example 2.6.1, parts A and part B. We just didn't do part B. So this is why we consider the x approaching positive and negative infinity at the same time in hindsight. This works because I know what 1 over x does when x approaches positive infinity and negative infinity. In both cases, it gives out a limit of 0. So I replace this limit, this limit, this limit, and this limit with 0. So we get 0 there. Here we had a limit of a constant function. Of course, that just gives the constant out. Same thing down here. So we get the 2's and the 1's from these. I want to plug all that stuff in and make sure we didn't get a 0 in the denominator. We didn't. We got a 1 in the denominator. And the value of that limit as x approaches positive or negative infinity. Both of those looks like are 2. So there's how you take a limit of a rational function as x approaches plus or minus infinity. Divide the numerator and denominator by the highest power of x in the denominator. You divide it by the highest power of x in the numerator. Well, this time it didn't matter because they were the same. But you might end up with some zeros in the denominator, so that won't work. Divide numerator and denominator by the highest power of x in the denominator. And it'll work out just like this one does, provided you have a rational function. Let's look at another one. Okay, this ain't a rational function because of the square root. It says evaluate the limit as x approaches negative infinity. Okay, just one direction this time. 4 minus 3x cubed over the square root of x to the 6 plus 9. By dividing the numerator and denominator by the effective highest power of x in the denominator, and justify your computations like we did in the last one. All right, what's up with this effective highest power stuff? And I think that's my hint. That's not in the book. In the denominator, we've got an x to the 6. Actually, we got a square root of an x to the 6 plus some other stuff. My claim is the effective highest power of x, then, square root of x to the 6 will be x cubed. Highest power of x in the denominator is effectively 3. What happens when x is really large? If x is a big number, x to the 6 plus 9, that's about the same size as x to the 6. The plus 9, it ain't going to matter much. For example, dude, if x was 10, 10 to the 6th power, that's 1,000,000. So we'd have not 1,000,000, but 1,000,009. So the 9 doesn't contribute much, even when x isn't that big. The 9 doesn't contribute that much. So this is informal, but this is how you need to think of it. X to the 6 plus 9, about the same size as x to the 6. You take the square root of it, that's going to be about the same size as x cubed. The plus 9, when x is big, isn't going to contribute much. Wink. Wink means I'm being informal, trying to give you an idea of how to work these. So I claim the effective highest power of x in the denominator is 3, and x cubed. All right, so let's multiply the numerator and denominator by 1 over x cubed, dividing numerator and denominator by the effective highest power of x in the denominator. It's not entirely a coincidence, it's the same as the power of x in the numerator. But multiply by the 1 over x cubed divided by itself. You didn't divide by 0, right? Right. X approaches negative infinity. Well, I can assume that x is not 0. Okay, so let's see. We'll simplify that a little bit. We'll need to distribute next. Okay, there's the term, the expression from the previous slide. We need to distribute, I guess, first. Let's take this x cubed. I won't put it under that square root. We're going to do it like this. Let's take x cubed and replace it with negative square root of x to the 6th. Are those the same? Remember, x is negative. Let's see, square root of x to the 6th, that's not simply x cubed. We've been through this. Remember, square roots are never negative. The square root symbol means take the positive square root. All right, then the square root of x to the 6th, that's positive. X cubed, could x cubed be negative? Yeah, if x is negative, then x cubed will be negative. Negative times a negative times a negative is negative. Is x negative? Oh, it is. X approaches negative infinity, so effectively x is negative. X is negative and big if we take into account the specific definition of limit. So we need x negative. All right, well, if I take the square root of x to the 6th, I don't get x cubed, I get the absolute value of x cubed. The square root is absorbing any negative signs in a sense. With the squaring that comes with the x to the 6th combined with the square root, you get stuck with an absolute value. How do you get rid of it? We were talking about this a second ago. Well, if x were positive, then x cubed would be positive, and we just drop the absolute values. What if x is negative? Then this quantity x cubed is going to be negative. How do you make it positive? Because the absolute value is going to make it positive. I'm trying to drop the absolute values. I can't just drop them. That's wrong. I'll be off by a negative sign. I'm trying to replace them with something else. Well, how do I change something that's negative, like x cubed, into something that's positive, like the absolute value of x cubed? Change its sign, multiply by negative. So then, had x cubed been positive, then negative x cubed would be negative. Had x cubed been negative, which it is in this case because x is negative, then negative x cubed is positive. That thing's positive, it better be, it equals an absolute value. Or if you like, it equals the square root of something. It better not be negative. It ain't negative. It's a product of two negatives. This -1, that's a coefficient out front, and this negative x cubed. Remember, x is negative, so x cubed is negative. This is a negative times a negative, which is indeed positive. So that's the tricky part on this one, is getting rid of the absolute value that pops up when you try to get this x to the 6th under the square root. This one's particularly tricky with that. These are ideas you've been exposed to before. They're subtle ideas. So you might want to replay this video a couple of times because that is a subtlety, but that's what you get when you take the square root of x to the 6th when you're dealing with x as a negative number. And that's exactly what we're doing. Why do we put a square root on this thing? Well, I want to get that, that inside this square root. So that's why we're doing this. Okay, well then we've got a square root and a square root. Combine them. We got a negative sign floating around. Let's move that out front. There it is. And now we've got the square root of x to the 6th plus 9, quantity, divided by x to the 6th. We combine the x to the 6th in the denominator with the x to the 6th plus 9, in the numerator. They're both under square roots. Combine them under a single square root. That's a legitimate operation. Now let's distribute. Okay, so now we can do the distribution stuff. I might pause briefly to say, what are we looking for? You're looking for a limit of 1 over x, because that's the limit you know. So we're trying to get a 1 over x out of all of this by dividing by the highest power of x in the denominator. You'll be seeing 1 over x's. So we get distributing, take the x cubed divided by x cubed in the numerator, distribute it over each of these, take the division by x cubed times 1 over x, sorry, x to the 6th, distribute that through those other two terms in the denominator. It's division. No need to justify that, it's just distribution. And now can you cancel powers of x? Yeah, as long as x isn't 0. It ain't 0, it's a big negative number is the idea for this kind of limit. So x being a big negative number, x is not 0. We can cancel these two x cubes. They're gone, replace with 1. We can cancel these two x to the 6th. They're gone, replace them with a 1. Nothing to cancel here or here, so we're kind of stuck with those. But looking at this, you ought to be liking what you're seeing. There's a 1 over x. Okay, there's a 4 in the way and it's actually cubed, but there's a 1 over x. It's actually 3 of them somewhere in here. Here's another 1 over x in a sense. All right, we just got to get the limit to those 1 over x things. Okay, we got a quotient, or the limit of the quotient is the quotient of the limits. Quotient rule for these infinite limits. Theorem 2.12, part 5. What's next? In the numerator, I'll use a difference rule. I'll probably bring a constant out, and I'll use a root rule to get a 1 over x cubed. Down here, we got a square root. I say root rule, sorry, I use the power rule up there. I use a root rule down here where we've got the root. So the plan is to get this limit on each of these individual pieces, justifying as we go using theorem 2.12. Okay, so we left off with a limit of a difference and a limit, we got a negative here. How about next? Maybe bring that negative out of that limit. It's constant multiple. I think that's what we'll do next. Yeah. So let's take the limit of the difference in the numerator and write it as a difference of limits, difference rule, and that negative that was inside the limit, yeah, let's bring that out. Constant multiple rule justifies that. So let's see. This is a constant, so I know what will happen there. We'll evaluate the limits all in one step, just that's a courtesy. That 4's in the way. I want to get rid of it, get it outside of the limit. I can do that. And I don't like that cube. We'll take care of that as well. First, let's do something else with this denominator. Can you take that limit inside that denominator? Yeah. Root rule says take the limit inside the denominator. Okay. It's gone inside a square root function. Are you sure 1 plus 9 over x to the 6th? That's never negative when x is big? It's never negative at all. It's 1 plus something, and the something is positive because of that 6th power there. Root rule, it's good to go for that one. So indeed, you can take the limit inside the square root. That's the hard one to check on the details, but details are satisfied. We're not getting square roots and negatives, so we're good. All right, let's see, we'll probably need to break that up using the sum rule. Let's do that next. We'll break the stuff under the radical up using the sum rule. Let's bring that 9 outside using the constant multiple rule, and let's bring that 4 outside also using the constant multiple rule. So I did 2 or 3 steps of algebra on that one. 2 or 3 steps of calculus, justified by Theorem 2.12. So we broke up this as a limit of a sum as a sum of 2 limits, and brought the 9s and the 4s out front as constants. And there's why we can do that. And semi-finally, let's take this limit of 1 over x cubed and write it as a limit of 1 over x cubed. Same thing with this limit of 1 over x to the 6th. Limit of 1 over x to the 6th. Who says? It's the power rule that allows you to do that. Okay, so we're passing those limits inside those raising to the 3rd power and raising to the 6th power functions. Power rule says you can do that. And that's what we were looking for. Here's a limit of 1 over x. I know what that is, it's 0. Here's a limit of 1 over x. I know what that is, it's 0. There's a limit of a constant and a limit of a constant. I know what those are too. Okay, so recopying where we left off. This is the last line from the previous slide. Limit of 1 over x goes to 0. Limit of 1 over x goes to 0. 0 cubed and 0 to the 6th. Let's write that out so you can see where everything came from. Constant goes to the constant of 3. This constant goes to 1. Don't forget that negative sign that was looming around out front. Numerator gives us -3. Denominator gives us -1. And so the limit is 3. Take it all the way down to here. We've done 2 of these, and I've written the denominator out both times. Make sure we ain't getting 0 in the denominator. How do we do this? By multiplying numerator and denominator by 1 over the highest power of x effectively in the denominator. You use the effective highest power in the denominator, then you won't get zeros in the denominator. Just checking to make sure everything worked out. And if I had a rational function, then we wouldn't have the square root. Square roots don't appear in rational functions. Then I wouldn't have to use this effective word. We just use the highest power of x in the denominator if we had a rational function. We don't. The square root messed it up. You know, it didn't mess it up too much. We were able to mimic what we would do for a rational function. So this is a little more general in this case. Back to the notes. So we got through those 2 examples. Okay, we're going to define what it means to have a horizontal asymptote of a graph. You've dealt with horizontal asymptotes before. I fear that you may have been told some wrong terminology or told some terminology that's stuck in your head in the wrong way. So we'll fix that. It's hard to talk about asymptotes. Even though you do it in pre-calculus, it's hard to talk about it without calculus. So you sidestep some of the details in pre-calculus, not a problem. We'll take care of those details in here because we got the equipment, because we've got infinite limits. So we take our first step, but certainly not our last, and using calculus to graph a function by defining what it means for a function to have a horizontal asymptote. A line, y equals b, is a horizontal asymptote of the graph of the function y equals f of x if either the limit as x approaches positive infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. So finding horizontal asymptotes is evaluating these kinds of limits. Let's do one. So we'd like what we just did, except this go round, it'll probably come to us as a question about horizontal asymptotes. Well, then we'll change it into a question about infinite limits. Let's actually do 3 examples. Okay, find the horizontal asymptotes of the graph y equals 2x over x plus 1. Justify your computations like we've been doing. Okay, that's a rational function, a ratio of polynomials. So we're going to consider a limit as x approaches plus or minus infinity of this. The positive and negative infinities for rational functions, they'll be the same. We'll get limits of 1 over x, we'll be good to go. Other more exotic functions, like that example we just did with the square root of the x to the 6th stuff, that one would have behaved differently if we go in the positive or negative direction. Something happened with that absolute value function. So for rational functions, ratios of polynomials, you can consider a limit as x approaches positive and negative infinity together. They'll be the same. Other functions, I can't make any promises. In this case, we'll take the rational function, divide the numerator and denominator by the highest power of x in the denominator. So I'm attracted to this x to the first power there. So we'll multiply by 1 over x, divided by 1 over x. Usual story, x is big, it's not 0. This is defined, and it equals 1. So we haven't changed the question. Let's distribute those things in the numerator and denominator. Further distribute. We got an x over x in a couple of places. Can you cancel those x's? Yeah, as long as x isn't 0. X ain't 0. It's a big positive or a big negative number, so it's not 0. So we can do the cancellation of the x's. X approaches plus or minus infinity. We can assume x is not 0. That justifies the cancellation. Okay, here's where we left off. Limit of a quotient is a quotient of the limits. As long as we don't get 0 in the denominator, you won't, because you cleverly divided by the highest power of x in the denominator. That'll avoid this getting zeros in the denominator later on. We've got a sum in the denominator, so we'll write the limit of the sum as the sum of the limits. Got a constant up top, and it looks like we're good to go. We didn't have to deal with the power rule in this one. It was actually a little bit easier. What happens to 2 when x gets large in the positive or negative direction? Doesn't care, it's too busy being 2, it's constant. So we get the 2 out there. Similarly, we get the 1 out there. What do you know about limits as x approaches plus or minus infinity? I know 1 over x goes to 0. So this limit, by the example we did, goes to 0. Both in the positive and the negative direction. We only proved half of it, but the other half is proved in the book. So we got a limit as x approaches plus or minus infinity of this function equals 2. That means y equals 2 is a horizontal asymptote of the graph of this function. We'll graph functions here soon, and we've got a very good technique to find horizontal asymptotes. You probably had this technique in pre-calculus, and you looked at highest powers of x in the numerator and the denominator. That's ultimately what we're doing. But we can do more than rational functions because we can take limits of more than rational functions of this sort. Find the horizontal asymptotes of this graph. Justify your computations. This is a rational function. No, the absolute value messes it up. Rational function will have only one horizontal asymptote. Here, we're not given a rational function. The absolute value messes up this being a rational function. If the absolute value wasn't there, we'd be good to go with a rational function. So this time we're going to have to consider limits as x approaches infinity and negative infinity separately. Well, we'll do the same technique of dividing numerator and denominator by the effective highest power of x in the denominator. Looks like x cubed. It's the absolute value of x cubed, so that's going to have some implication. But in starting the manipulations, we'll divide numerator and denominator by x cubed. And what we've got in the denominator here, that is x cubed when x is positive, and it's the negative of x cubed when x is negative. We'll have to get rid of that absolute value, and that's how we'll do it. So let's take a limit as x approaches positive infinity. Okay. We'll divide numerator and denominator by the effective highest power of x in the denominator. So it's effectively x cubed. Distribute, you get x cubes here. X cubed over x cubed, we can cancel those, provided x isn't 0. It isn't 0, it's a big positive number. oh, x is approaching positive infinity, then x is positive. And the absolute value of x cubed is the same as x cubed when x is positive. You can drop the absolute values. We check that because x is positive. So I'll replace the absolute value of x cubed with simply x cubed and distribute at the same time. That'll give us an x cubed over x cubed here. We've got the -2 and the +1s both divided by x cubed. So that leaves us here. What will you do next? We'll cancel the x cubed. What are you looking for? Looking for a limit of 1 over x. Trying to get 1 over x's out of these things because I know what those limits are. Okay, here's where we left off on the previous slide. Cancel the x's. I can cancel these to get a 1. I can cancel these to get a 1. So I can't do anything here. Nothing to cancel there. You sure x is not 0? I'm sure x is not 0. X is approaching positive infinity, so it's a big positive number. Think of it like that. Limit of a quotient, hey, that's the quotient of the limits, as long as we don't get 0 in the denominator. I don't think you will. Let's take this limit and use the difference and sum properties. You're not distributing because you're not multiplying. But we get the limit of the difference is the difference of the limits in the numerator. The limit of the sum is the sum of the limits in the denominator. It's the sum rule and difference rule for infinite limits. It's given in the theorem. It's not distribution. You won't think about it as distribution. Just don't tell me about it. And that's not a bad way to remember it. It's not distribution because you're not multiplying. It's the sum rule and the difference rule. But whatever goes on in your head that helps you understand this, I can't complain about it. Just don't tell me about it because it's not distribution. It's something else. All right, what's next? See that 2 there? Let's get rid of that 2. Let's bring it outside. Next slide, bring the 2 outside. You can do that by the constant multiple rule. That'll leave you with a, let's go back. We then had a limit of, there was an x cubed in there going forward. Let's take that limit inside the cubing function, both in the numerator and the denominator. The power rule justifies that. Constant multiple rule, let us bring the 2 outside. So I'm working these in a less detailed way as we do more of them. So we've got to save time somehow. That's a power rule that let us take the limit inside the cube, the numerator and denominator, and that's what we were looking for, a limit of 1 over x, because I know that's 0. So constant has a limit of 1, constant has a limit of 1, minus 2 times. This has a limit of 0, so does this. We get zeros there and there. Notice we get 1 divided by 1. We didn't get 0 in the denominator. We're good. We get 1 out. Example 2.6.1 justifies the substitution of the zeros there, part A, actually. So this function has a horizontal asymptote of y equals 1 as x approaches positive infinity because the limit was 1. The limit as x approaches positive infinity of f of x equals 1, y equals 1 is a horizontal asymptote of that function. But this is only half of it. We got to consider a limit as x approaches negative infinity as well. Well, it's largely the same, but for one little part. The computation is similar when x approaches negative infinity, except x is negative now. So when we look at the absolute value of x cubed, and that thing, that's positive. But if I cover this up, x cubed itself would be negative. Whoops, because x is negative. So we need to insert another negative to make it positive. Is negative x cubed, is that indeed positive? Yeah, it's a product of 2 negatives. The negative out front, and remember, x is negative because x is approaching negative infinity, so it's a big negative number. We've got a negative times a negative. X cubed is negative because x is. So negative x cubed is itself positive. Product of negative times negative is positive, as it should be, to relate it to the absolute value on the other side. So again, it's the second time we've seen this kind of thing. We can get rid of the absolute values by treating it appropriately. You can't just drop them in this case. You could when x was positive, because you were dealing then with known positive quantities. Well, I can still get rid of them because I'm dealing with known negative quantities now. I just have to be a little more subtle. So when we look at the limit, we'll do the same computations. Same as before, except now we're going to replace the absolute value of x cubed with negative x cubed. So take this, replace it now with a negative x cubed, do the distributions, the division by the x cubes throughout. Can you cancel? Yeah, because x is not 0. X is approaching, it should read approaching negative infinity. Let's see, actually there's typos throughout this. X is approaching negative infinity here. I'm a victim of cut and paste. X is approaching negative infinity. So we're taking x to be negative. You can simplify, you can cancel the x cubes over x cubed, x approaching, negative infinity. So x is non-zero. So cancellation is justified. So except for the substitution of absolute value of x cubed with negative x cubed, it's the same as we had before. It's why I cut and pasted it and messed up. Still got a quotient rule, write it as a quotient of limits, provided we don't get 0 in the denominator. We won't. Something will be different from before though. I can use a sum and a difference rule to get that limit on each of these. And it pains me to see that I left the negative sign off of all these infinities. I'll modify that and get it online. As before, we'll bring the 2 outside, constant multiple rule. As before, we'll take the limit inside those cubing functions, so quite similar to what we did before. Constants will produce the obvious thing. We were looking for a limit of 1 over x. We got it cubed in fact. We'll get zeros out of that. Example 2.6.1. It's actually part B because I should have x approaching negative infinity. That will produce that. And so this time we got out a limit of negative 1. So this function has a horizontal asymptote of y equals negative 1. I got it right here. As x approaches negative infinity. Limit as x approaches, negative infinity of the function equals negative 1. Then y equals negative 1 is a horizontal asymptote. So this one does different stuff when x is big and positive versus when x is big and negative. In one direction, it had a horizontal asymptote of positive 1 when x was approaching positive infinity. And when x approaches negative infinity, it's got a horizontal asymptote of negative 1. So it does different things in different directions. That won't happen for a rational function. Whose fault is it that it did different stuff in different directions? And it comes down to the presence of that absolute value there. If that absolute value wasn't there, it'd be a rational function and we wouldn't have this kind of unusual behavior of one limit in the positive direction and a different limit in the negative direction. That won't happen for rational functions, but it can happen. It just did. We got 1 out from one side and negative 1 out from the other side. You want a cleaner function that behaves like that. This isn't quite the time or place, but the inverse tangent function behaves that way. Take a look at tangent inverse, and you'll see it does one thing as the input approaches positive infinity, and a different thing as the input approaches negative infinity. Tangent inverse, a relatively simple function, behaves differently, just like this one did. So I don't need the trick of an absolute value to get that kind of behavior. We're not quite ready to deal with trig functions just yet in this setting, though. And let's do another formal proof involving the exponential function, depending on, so I'm relying on your knowledge of the exponential function and what a graph looks like. Use the formal definition to prove the limit as x approaches negative infinity of e to the x equals 0. Limit 0, that means y equals 0 is a horizontal asymptote of the exponential function. You know what an exponential function looks like, so this shouldn't come as a surprise to you. And this only holds in the negative direction. First, domain of e to the x, it's all real numbers. So there is an interval of the form negative infinity to p, where the function's defined. It's defined everywhere. So in particular, it's defined for large negative input values. So we've got the function defined where it should be. using the formal definition. We'll let epsilon be greater than 0. We need to find a capital N, blah, blah, blah. I say choose N to be the natural log of epsilon. All right, never mind why just yet. We'll look at a picture and explain why, but that's the logic. Epsilon is given to you, and then you choose an N based on that epsilon. I'm choosing N to be the natural log of epsilon. Let's see if it works. Then if x is less than capital N, which we've taken to be the natural log of epsilon, let's exponentiate both sides of this equation. That'll give us an e to the x on the left and an e to the n, or an e to the natural log of n on the right-hand side. What is e to the natural log of n? Why? The exponential function and the natural log function are inverses of each other. That's where the log function comes from. So we'll just get the epsilon out. Exponential function is an increasing function. You put bigger things in, you get bigger things out. Increasing function, actually here's the graph of it. Yeah, the exponential function is an increasing function. So if I put something bigger, like natural log of n in, I'll get out something bigger versus putting something smaller like x in. So the inequality is preserved there because we're dealing with a function that increases as we read from right to left, from left to right. So that gives us a relationship, e to the x is less than epsilon. So if x is less than n, then we get e to the x is less than epsilon. If x is less than n, e to the x is less than epsilon. That's what this says. Of course, I want to make it look like an f of x minus L type thing. E to the x is the same as the absolute value of e to the x minus 0, ain't it? Yeah, the minus 0 doesn't do anything, and exponentials are never negative. So I don't need, I can insert absolute values if I like. Look at the graph. It's actually always positive. And e to the x is the function we're interested in, the f of x function, and the alleged limit L is 0. So we've got f of x minus L is less than epsilon. X less than n implies f of x minus L less than epsilon. That's the very definition of the limit as x approaches negative infinity, negative because of the x less than n. X approaches negative infinity of e to the x equals L equals 0. So there's a proof by definition. Where did this choosing n equals a natural log of epsilon come from? Let's look at the graph. If you know the graph, you can figure it out. Here's what an exponential function looks like. We were trying to get over here on the left-hand side where this green box, green bar is, we were trying to get the function to lie inside that green bar. From 0 plus epsilon really to 0 minus epsilon. I know it never goes below the x-axis. So the book's chosen to leave that out, but I wouldn't mind if they went from negative epsilon to positive epsilon. They got their reasons. But we want the blue function over here to lie inside the green band. All right. Well, when would you get epsilon out of the exponential function? When you put the natural log of epsilon in. Put natural log of epsilon in, exponentiate that, put it inside the exponential function, you'll get the epsilon out. Natural log function and exponential function base e, they're inverses of each other. Logs and exponentials are inverses of each other. So the input would have to be natural log of epsilon. So that's why we chose n to equal natural log of epsilon. It's this picture. Granted, in the picture, it doesn't look like n is a big negative number. If I made epsilon smaller, I'd have to scoot things over here to, keep the blue stuff inside the green band, as always. But for the sake of a picture, if I make epsilon sufficiently small, I get the n really big, and so you're not going to be able to see the picture. But the idea is still n is a big negative number. All right, so let's see. Take care of the examples. Yeah, so we did those 3 examples. Some other things that carry over from the past is Theorem 2.10. You can take limits inside continuous functions. That also holds for x approaching plus or minus infinity in the following sense. Let me call this Theorem 2.6.a. The book doesn't explicitly state it. They mention this in passing, and here's what they mean. If g is continuous at the point b, and the limit as x approaches plus or minus infinity of f of x equals b, then the limit as x approaches plus or minus infinity of the composition function, g composed with f of x inside the g function, equals g of b, or in other words, equals g of the limit as x approaches plus or minus infinity of f of x. You can take the limit inside the g function because the g function is continuous. It's computationally best to think that's what continuity is. You can take limits inside continuous functions, even when x approaches plus or minus infinity. Now, there's a setting here in hypotheses, but let's illustrate that with the following example. An example, let's see, 2.6.a, I probably made this one up too. Show the limit, or evaluate the limit as x approaches positive infinity of cosine 1 over x. Okay. We know the limit as x approaches infinity of 1 over x equals 0. We proved it. We've shown, I guess it was exercise 2.5.72, I think this is in the notes even, that the cosine function is continuous everywhere. Of course it is, you know that from your previous experience, but we justified it with calculus. So in particular, cosine is continuous at 0. All right, limit as x approaches infinity of 1 over x equals 0. The cosine function is continuous at 0. Then the limit as x approaches infinity of cosine 1 over x is the same as a cosine of the limit as x approaches infinity of 1 over x. You can take that limit inside that cosine function because it's continuous at the limit value. The limit value is 0. Cosine function is continuous at 0. It's continuous everywhere. Continuity at 0 is what matters here. And the cosine of 0 equals 1. So there's the limit. So that one's actually quite easy. But it illustrates that theorem 2.6.a. Whoops, back to the notes. All right. Sandwich theorem also holds for limits as x approaches plus or minus infinity. Same hypotheses, except with this infinity stuff playing a role. Suppose g of x is less than or equal to f of x is less than or equal to h of x. So f of x is sandwiched between g and h for all x in some open interval of the form p to infinity. So there's your open interval. Says this inequality holds for sufficiently large input values, sufficiently large x. And that's what you look at when you look at limits as x approaches positive infinity. Suppose the limit, so this is hypotheses, the limit of the g function as x approaches infinity and the limit of the h function as x approaches infinity are the same, and they're that value L. F is sandwiched between g and h. G and h have the same limit L, this time as x approaches positive infinity. Then the limit as x approaches positive infinity of f of x is also the value L. Same kind of thing we had with the ordinary sandwich theorem, except for this interval stuff and x approaching positive infinity. And we could say the similar type thing if we wanted to consider limits as x approach negative infinity. We just have to change it to having the inequality hold for sufficiently large negative x values on an open interval of the form negative infinity up to p. So this includes arbitrarily large input values x that are negative. And it's the same type of conclusion, of course. If g and h have the same limit, then f has that common limit L. Let's illustrate that as follows. Okay, use the sandwich theorem to find the horizontal asymptote of the curve y equals 2 plus sine x over x. Okay, we're going to use the sandwich theorem because I know how big sine function gets and I know how negative a sine function gets. That sine function is always between -1 and 1. So we can bound the sine function part above by 1 and below by -1. Sine function always between -1 and 1. So let's define a g of x function to be 2 plus negative 1 over x. So I'm replacing the sine function with its lower bound and negative 1 and getting 2 minus 1 over x. And let's replace the sine function with its upper bound of 1, and we'll get 2 plus 1 over x. Actually view them both as, excuse me, as 2 plus negative 1 over x, and 2 plus positive 1 over x, with the negatives and the positive playing those roles. Then, since the sine function is sandwiched between negative 1 and 1, then the f of x function, 2 plus sine x over x, will be sandwiched between the g and the h function. G of x is less than or equal to f of x is less than or equal to h of x. So we get that sandwiching, and this will hold everywhere. Well, except at 0, because we can't let x be 0. So this actually holds for all x values. We're worried about horizontal asymptotes. We're worried about x big and positive or x big and negative. Well, that sine function is always bounded by this. So this will work for all x values, well, except for 0, since the f function isn't defined at 0. Neither is g or h. So this holds in particular on an interval of the form negative infinity to p. We could take p to be 0, say, and p to infinity. Now we could also take p to be 0 there, or other things. All right, so we need to see if g and h have the same limits as x approaches plus or minus infinity. They do. Limit as x approaches plus or minus infinity of g of x, that'd be 2 minus 1 over x. Let me skip some of the steps, we've done a bunch of this. The 2 is a constant, no surprise there. And then we get a limit as x approaches plus or minus infinity of 1 over x. That's going to go to 0. In the limit, we'll have 2 minus 0, so we get a limit of 2. When I look at 2 plus 1 over x, that is the h of x function, the upper bound. Similar behavior, now we get 2 plus 0. 2 minus 0 versus 2 plus 0. Be conscientious about these signs to show you where things came from. But in both cases, we get a limit of 2 out. As explained by example 2.6.1, the one thing we know about infinite limits is what 1 over x does, which is why they could ask us about something involving 1 over x. So by the sandwich theorem, theorem 2.6.b, the limit as x approaches plus or minus infinity of f of x is also going to be 2, valid for both x approaching positive infinity and negative infinity. We've actually established 2 limits here, arguably, and we've combined them as 1. And they're both 2 because g and h both had limits of 2. So y equals 2 is a horizontal asymptote of the graph of this thing. This time it does the same thing in the positive direction as it does in the negative direction. The function gets close to 2 in a sense. Okay, I chose to do this one for the following reason. Going back to the notes, let's actually look at a graph of y equals 2 plus sine x over x. So let's take that one, talk about it a little bit. We just saw this as a horizontal asymptote of y equals 2. Okay, here's a thing I'm worried might be rattling around in your head. Let's get it out of your head if it's in there, because it ain't right. And I'm a little loose on some things, like if you want to think that you've distributed that limit, you didn't, but if it helps you remember it, fine. This is a conceptual flaw. You may have heard it said before that an asymptote is something a function gets closer and closer to, but it never gets there. I'm going to convince you that ain't the case, because we just saw a function that has an asymptote. This 2 plus sine x over x has a horizontal asymptote of y equals 2. And none of this is true. Y doesn't get closer and closer to 2, and it does get there. Now, this only claims 2 things. Gets closer and closer, but never gets there. This is just wrong. The highlighted stuff is wrong. You can't take that as an idea in general for, say, a horizontal asymptote. If we had a rational function, you might be able to recycle this if you were careful enough and get some mileage out of it. But it's not what a horizontal asymptote is. Let's look at the graph of y equals 2 plus sine x over x. Okay, it's a figure out of the book. Let's make it a little bit bigger, or a lot bit bigger. Does this graph have a horizontal asymptote of 2? Yeah, it gets close to 2, and it stays close to 2. How close to 2 would you like to get it? You tell me, epsilon, how close you want this blue thing to get to this horizontal red line, and then I'll tell you how far we have to go to the right or the left. That is, I'll give you a capital M on this side and a capital N on that side, such that I'm going to draw a little green band, and eventually, heading off in the positive direction, the graph would lie inside the green band and stay inside the green band. Eventually, on the negative direction, the graph would lie inside the green band and stay inside the green band. So what a horizontal asymptote really is, if you want something informal, it says this on the previous page, is that the graph gets close to the asymptote and stays close to the asymptote. There is no closer and closer and never gets there. Does this blue function get there? Does it take on the value 2? Yeah, it does there and there and there and there. In fact, this is happening every pi radians. At pi, the value is 2. At 2 pi, the value is 2. At 3 pi, 4 pi, 5 pi, 6 pi, all integer multiples of pi, except for 0, where some other stuff's going on, this thing is taking on the value 2. So never gets there. No way. It gets there an infinite number of times. You can't get any closer to 2 than 2. It does get there. So that part ain't right. How about the getting closer and closer stuff? Well, look at this. Here it comes. It's getting closer and closer to 2. You say, oh, we got there. Now it's going away. So it ain't getting closer and closer. For x values between here and here, it's actually going away. The important thing is it stops, and it turns around, and it comes back. And it gets closer and closer. Actually takes on the value. Now it's going away again. But it turns around and comes back. It gets there. It goes away again, but it doesn't go very far away. Not going very far away is what matters. So this is explained in terms of intervals upstairs, but the real story is in the picture. So this function has a horizontal asymptote of 2 because it gets close to 2 and stays close to 2 informally. Formally, it's all the epsilons and the capital N's and capital M's stuff. But this does that. And it does get to the value 2 an infinite number of times, in fact, and it's not always getting closer and closer. Sometimes it's getting closer, sometimes it's getting further away, as I maybe read this as x changes in the positive direction or the negative direction. It has a symmetry, of course. So closer and closer, nope. Never gets there, nope. Gets there infinitely many times. Half of the x values, it's even going away from the asymptote. It's not about closer and closer. It's about getting close and staying close. When it goes away, don't go far away. It stays close. In fact, it turns around and comes back. Then it goes further away again, but even less far away, as would be necessary for this to be a horizontal asymptote. So back to the previous page, I think I covered all of this. It gets to the value 2. In fact, it gets to the value 2 every integer multiple of pi, except at 0, where we had division by 0, so there's a problem there. Some of the time it's, getting further away, and some of the time it's getting closer. If you want something informal about an asymptote, it's something the function gets close to and stays close to. Here's where, if this is in your head about closer and closer but never gets there, here's how it got in your head. It's a trig function that's allowing this thing to oscillate. If I dealt with rational functions on one side, eventually you'd see it getting closer and closer to the asymptote and never getting there. On the other side, eventually you'd see it getting closer and closer to the asymptote and not getting there. Now it can get there somewhere else, but eventually you'll see it asymptotically approaching, in the sense that you're used to thinking of closer and closer but never gets there. Out on the sides, it'll eventually behave like that if it's a rational function. But if it's not a rational function, it can behave in a more exotic way. Closer and closer, but never gets there is wrong. It's wrong for this example. So my work is done. It's wrong. But you will see lots of examples, they're rational functions, where closer and closer but never gets there is maybe applicable. And that's where this idea came from. And if it's in your head, it got in your head because you probably only considered rational functions when you were talking asymptotes the first go round. Welcome to calculus. You're a bit more mature these days, so I can tell you the truth. Want more details on this? I've published a little thing many years ago. This is like a page long that talks about these same types of ideas. I think it mentions a different function, but something basically the same. It's quite similar to what we did here. Let's look at one last example, and then we'll stop this video and start a new one to finish up the section. But let's look at 2.6, number 92. Okay, this is a little more involved than you might think by looking at. It says evaluate carefully, so I'm editorializing there. The limit as x approaches infinity of x squared plus x, square root of, minus x squared minus x, square root of. Justify your computations. All right. What do you want to see? You want to see limits of 1 over x. Okay, I got some bad news for you. There ain't any division in this thing. So I don't know how you're going to get a 1 over x when you ain't got any division. Let's introduce some division. All right, so I'm trying to motivate the following manipulation. Let's multiply by the conjugate of the given expression divided by itself. So we're simply multiplying by a version of 1. So we're going to take this limit and multiply by conjugate. You're used to this idea from rationalizing denominators, maybe. Take the minus a square root thing and replace it with plus a square root thing. So we'll have x squared plus x square root of plus x squared minus x square root of divided by itself. Multiply by that thing. We okay on this being defined for x sufficiently large? Yeah, only thing that could go wrong is, let's see, at x equals 0, you'd have division by 0. But we're taking x to be arbitrarily large, so problems at 0 ultimately won't affect our limit. And I'd be worried about square roots and negatives. And if x is big enough, this is bigger than or equal to 1, we won't have square roots and negatives. So for x sufficiently large, we're good. This is defined, no problems. And sufficiently large is bigger than 1, so we're okay. All right, so let's multiply by that. Why, you might ask? Well, let me motivate it as I want fractions because I want to see a 1 over x somewhere in there. Also, I'm a little put off by these square roots. This will get rid of some of them, not all of them. Do your FOIL thing, okay, the fact that we've got quantity, thing 1 minus thing 2 times thing 1 plus thing 2, we'll get the first one squared minus the second one squared. That's why we did this stuff with the square roots. In the denominator, we're just stuck with whatever it is we've introduced. But in the numerator, we'll get rid of some square roots. Okay, we get the square root of quantity squared in both cases, so we can drop the square roots. We're left with x squared plus x minus x squared minus x. All right, you can't argue with the validity of it. My motivation is I want to get rid of the square roots and I want to see fractions. I want to see 1 over x. We'll see 1 over x. We have to. It's the only thing we know. Let's see, the x squares cancel. We're left with 2x in the numerator, so we'll simplify that. So we've got it down to here. How do you feel about that limit? Think you could get some 1 over x's there? We did one like this before. I'd talk about dividing by the highest power of x in the denominator if it was a rational function, but it isn't because of the square roots. Fine. How about divide by the highest power of x, effective highest power of x in the denominator. Here's where we left off. It's a similar argument to what we had before. You get the square root of x squared plus some smaller stuff. I say x to the 1 is effectively what we have in the denominator. The highest power of x in the denominator, the effective highest power, is x to the 1. So let's divide numerator and denominator by x to the 1 power. Okay, if we get division by 0, then I've had a bad idea. So let's see what happens. So this has worked similarly to the others. The trick was introducing something that gave us a quotient. We got to have quotients. All right, we'll distribute in the numerator 2x over x. We get that 1 over x in the denominator. Remember, x approaches, x approaches positive infinity. So how about I take this x and write it as the square root of x squared? What is the square root of x squared? Ooh, that's the absolute value of x. Is that the same as x? It is if x is positive. X is positive. X approaches positive infinity. We could probably, if we took a limit as x approaches negative infinity, do a similar thing. But stuff would change right here if we had x negative. We don't. We've got x positive. So we can replace x with the square root of x squared because that's the absolute value of x. And when x is positive, that's the same as x. So legitimate substitution. Why would you do that? To get the x squared underneath common square roots. So we'll distribute the divided by square root of x squared thing to get a square root divided by a square root and another square root divided by a square root. As we left off on the previous page, we can, not as left off, we've combined it. So we go back to the previous page here. Okay, we had a square root divided by a square root in 2 places. Here, we've got the square root of the division. So we've taken the 2 square roots and combined them, is what we did. So we've got combined square roots. That was the whole purpose of writing x as square root of x squared. Split things up across the addition and the subtraction, write it like this. And now we're in a good place to cancel x's. As long as x isn't 0, it isn't. X is a big positive number. We're taking that kind of limit. So cancel the x's in the numerator. You're left with a 2. X squared over x squared is 1. X over x squared, cancel one of those, and we're left with 1 over x. I was looking for 1 over x because that's the one limit I know. Similarly, we get a 1 here and a 1 over x here. Okay. Just got to get the limits to these 1 over x's. Everything else is a constant. All right. Limit of the quotients, quotient of the limits. Quotient rule. We got a sum in the denominator. Let's use the sum rule to get the limit on both of those. This is that thing I was talking about. You won't think of this as distribution. Just go right ahead. Don't tell anybody about it. It behaves like distribution. It's not distribution because you're not multiplying. You're taking limits. But if that helps you remember, whatever. All right. Now I need to get the limits inside these square roots. Root rule will let me do that, provided we don't get square roots of negatives. Okay, here's where we left off. Take the limits inside. Root rule. Hey, 1 plus 1 over x, 1 minus 1 over x. These are non-negative. Yeah, if x is greater than or equal to 1, these are non-negative. At x equals 1, this one we got no problems with because x is positive. This one, when x is 1, you get 0 out. 0 is non-negative. When x is bigger than 1, we got no problems. So no problems with square roots and negatives. So that's justified. All right, we got a limit of a sum and a limit of a difference. So we'll we'll use the sum and the difference rules and take that limit and put it on each of those parts. Not distribution, just kidding. And we got what we were looking for. Here's a limit of 1 over x. So that thing will be 0 and that thing will be 0. The other stuff is limits of constants. Fill it in. We end up with 2 over 1 plus 1. And we get out a limit of 1. All right, that was a little exotic. Once we got it started by multiplying by the right thing, it fell right into place for the techniques of infinite limits that we know. I could say the graph of that function has a horizontal asymptote of y equals 1. They actually ask us to evaluate a limit, though, if memory serves. Okay, so next we'll look at some other types of asymptotes, but I tell you what, let's take a little break because this has been a long one, and we'll come back and do a second video and finish this 2.6 stuff up. Have a nice day.